want to record one final video for this section in which I'm going to do two of the assigned problems from the homework. My hope is that if you can follow the reasoning and the thought process behind these problems, that it will help you understand some of the other problems on the homework that are similar but slightly different contexts. So let's start with number 24 in your text. Both of these problems have to do with normal distributions, and one of them has to do with the z-score. The first one we're going to do, 24, is actually dealing with the z-score. We're given two different scenarios of scores that people have done on a test, and we're asked between test A and test B, who had the better relative performance. So when we're comparing data points from two different tests, the way that we do that is through a z-score. So what we're going to do is we're going to calculate a z-score for test A, we're going to calculate a z-score for test B, and we're going to compare them. The way we're going to know very simply at the end of the calculation whose performance was better was simply by whose z-score is higher. As you may remember, the z-score measures how many standard deviations a score is above or below the mean. So the higher the z-score, the further this way above the mean they would be. The lower the z-score, the further the left of the mean. And so better relative performance would be higher up on the curve, more to the right of the mean. So to calculate a z-score, very simple calculation. We take our test score, so we're going to calculate the z-score for test A. I'm going to abbreviate ZA. We take our test score. For test A, that was 81. We subtract that from the mean, 74.3, and we divide that by the standard deviation, 3.6. That's not a formula I would expect you to memorize, but it is very simple. When you calculate that out and you do that division, you come up with a z-score of 1.86. If we repeat that process for test B, now our test score is 840. We always subtract our score from the mean, so minus 720, divided by the standard deviation, 146. And we do that calculation, we are going to come up with a z-score of 0.82. Comparing the two z-scores, 1.86 and 0.82, it's clear that the performance on test A was better because we have a higher z-score. If you want to understand that better in a graphical sense, if you were to plot those two, so direct your attention to this normal curve, this first dotted line is one standard deviation above the mean. So 1.86 would be almost two standard deviations above the mean, somewhere about right here. Where 0.82 would only be slightly less than one standard deviation below the mean, right about here. So clearly the 1.86 is a higher relative score than the other one. So we're just comparing two z-scores. The second problem that I want to do is number 30 from the book. 30 is in a real-world context. It's an interesting problem, and hopefully it shows you how you can use the idea of normal distribution and standard deviation in a real-world context. So, a light manufacturer advertises that the mean life of a light bulb that they produce is 2,400 hours. For that same light bulb, they have calculated that the standard deviation of life of the light bulb is 200 hours. And the question is, if you just go to the store and you pick up one of those light bulbs, what percent of these type of bulbs that are sold should be expected to burn longer than 2,600 hours? So our strategy is going to be to think about, what does 2,600 hours mean in relationship to a mean of 2,400 hours and a standard deviation of 200 hours? So there are a couple of different ways that we could explore that question. How does 2,600 hours compare to our mean of 2,400 hours and our standard deviation of 200 hours? One thing we could do would be to calculate a z-score. So we take our data point that we're interested in, 2,600, we subtract the mean, 2,400, and we divide that by 200. When you do that calculation, you end up with 200 over 200, which is just 1. A z-score of 1 means that 2,600 hours is exactly 1 standard deviation above the mean. You probably, in this case, wouldn't even need to calculate the z-score to see that. You should just be able to look and say, oh, 2,400 hours is the mean, 200 is the standard deviation, 2,600 is just 1 standard deviation above the mean. Now, we need to revisit our question. What percent of bulbs should be expected to burn longer than 2,600 hours? To answer that, we're going to use this chart that we've been coming back to over and over again in our book. So if 2,600 hours is 1 standard deviation above the mean, it's right here. Here's 2,600 hours. Here's the mean of 2,400 hours. The question is, how many bulbs burn longer than 2,600 hours? The bulbs that burn longer than 2,600 hours are all of those that lie in all of this region. Now, we're asked for a percent of bulbs, so it really is as easy as adding up the percentages in this standard deviation, this one, and this one, and you can see that those are gradually getting smaller. This isn't a chart that you have to memorize. You could just access it in your book. But in this first standard deviation, we have 13.5%. See that here? Then we have 2.35%. And then finally, in this little tiny tail, we have 0.15%. So the total percent of bulbs that lie in all of this region right here is 13.5 plus 2.35 plus 0.15, which turns out to be, 16%. So in answer to the question, we would expect that 16% of these type of bulbs could be expected to burn 2,600 hours or longer than 2,600 hours.